Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using Knime. In this chapter we're going to be talking about association rules, or what's otherwise referred to as market basket analysis. Market basket analysis has become one of the most common techniques among e-commerce websites. Start with the image of a shopping cart filled with numerous products purchased by somebody on a quick trip to the supermarket. The basket contains an assortment of products like orange juice, bananas, soft drinks, window cleaner, and detergent. One basket tells us about what one customer purchased at a time, but a complete list of purchases made by all customers provides us more information. It describes what are the most important part of a retailing business, what merchandise customers are buying and when. Market basket analysis uses the information about what customer purchases to provide insight into who they are and why they make certain purchases. Market basket analysis provides insight into the merchandise by telling us which products tend to be purchased together with other products. This information is actionable. It suggests new store layouts. It can be used to determine which products to put on special. It can indicate when to issue coupons and so on. When this data can be tied to another customer through a loyalty card or website registration, it becomes even more valuable. You know, the most common example you're going to see on this is going to Amazon.com. You go, you purchase a product, and what's the first thing Amazon shows you? These are similar products purchased by other people who bought your product. So that they start to say, look, people who bought hammers often bought nails. So they're trying to suggest and increase sales by showing you the most likely things you're going to want to buy next. All right, in this sample basket, the shopper purchased a quart of orange juice, some bananas, dish detergent, window cleaner, and a 6-pack of soda. Is soda typically purchased with bananas? Does the brand of soda make a difference? What should not be in the basket but is? Are window cleaning products purchased when detergent and orange juice are brought together? How do the demographics around the neighborhood affect what the customer buys? These are all questions we want to try to answer. Now, the data mining tool that is most closely aligned with market basket analysis is the automatic generation of association rules, a priori. Association rules represent patterns in the data without a specific target. Association rules were originally derived from point-of-sale data that describes what products are purchased together. Although its roots are in the analysis of point-of-sale transactions, association rules can be applied outside the retail industry to find relationships among other types of baskets. A rule like, if a customer purchases three-way calling, then that customer will also purchase call waiting, is clear. And even better, it might suggest very specific course of action, such as bundling three-way calling with call waiting as a single package for a carrier. While they're easily understood, they're not always useful. So the following are real examples of real rules generated from real data. Walmart customers who purchase Barbie dolls have a 60% likelihood of also purchasing one of 3 types of candy bars. A customer who purchases a maintenance agreement are very likely to purchase large appliances. And finally, when a new hardware store opens, the most commonly sold item is toilet bowl cleaners. Again, these are interesting rules, but how would you act upon them? What would you do with that information? In fact, those 3 rules really illustrate 3 common types of rules produced by association rules: the actionable, the trivial, and the inexplicable. The useful rule contains highly actionable information. Once the pattern is found, it's often not hard to justify, and telling a story can lead to insights and action. The trivial results are often already known and familiar to business, such as the sky is blue. And the inexplicable seem to have no explanation and do not suggest a course of action, like the third weird pattern. When a new hardware store opens, the most commonly sold item is toilet bowl cleaner. It's intriguing, tempting us, in fact, to provide information that does not give insight into customer behavior or the merchandise or suggest any further action. So let's put together some sample data here. I've got 5 customers, and I can see what each one of them has purchased. So example, customer 1 has purchased orange juice and soda. Number 2 has purchased milk, orange juice, window cleaner. 3 has orange juice and detergent. 4 is orange juice, detergent, and soda. And the 5th is window cleaner and soda. So these observations are example of associations and may suggest a formal rule, like if a customer purchased soda, then the customer also purchases orange juice. So what we want to find out is how good is this rule by looking at when somebody bought one item, what's the number of people who bought a similar item. Calculating the number of times that a given combination of items appears in the transaction data is well and good, but a combination of the items is not a rule. Sometimes just the combination is interesting itself, as is the example of the Barbie doll and the candy bar purchase 60% of the time. But in other cases, circumstances make more sense to find an underlying rule in the form of if condition then result. So this is a non-logical formulation of a hypothetical proposition. The condition is the antecedent, and the result is a consequent. Notice that this is just shorthand. If the rule says if soda, then orange juice, we would read it as if a customer purchases soda, then the customer is also expected to purchase orange juice. The measurement of support is the percentage of transactions that meet the condition and result. So in the data, 2 of the 5 transactions include both soda and orange juice. So these 2 transactions support the rule. So support is equal to the transactions that meet the condition and the result divided by the total number of transactions, or 2 over 5. In this case, so 40% of people who purchase orange juice also purchase soda. The confidence rule measures if the soda then juice, taking that statement, the confidence is the number of transactions that meet the condition and result divided by the number of transactions that meet the condition. So in this case, it's 2 out of 3, so 67% is my confidence level. 2 of these transactions that contain soda also contain orange juice. The inverse rule, if orange juice then soda, has a lower confidence. Of the 4 transactions with orange juice, only 2 have soda, so the confidence then is 50%. Now the probability measurement is if soda, then orange juice. Probability measures the number of transactions that meet the condition divided by the number of transactions. So the probability for soda is 60% of the transactions have soda, 80% have orange juice, 40% have soda and orange juice, and 100% have soda or orange juice. Now lift is a measure of how much better the chance is the rule if soda then orange juice. One way to answer this is to calculate lift, also called improvement, which tells us how much better the rule is at predicting the result than just assuming the result in the first place. So lift is a ratio of records that support the entire rule to the number that would be expecting, assuming that there is no relationship between the products at all. If the ratio of the density of the target, using the left-hand side of the rule, to the density of the target overall, so look at the formula. So is the probability of the condition and result divided by the probability of the condition divided by the result. So the probability of the condition and result divided by the probability of condition times result. So 0.40, if I'm looking at soda, orange juice, and an OJ, that 0.40 soda and OJ together divided by 0.6 times 0.8 is 0.83. So when the lift is greater than 1, the resulting rule is better than predicting the result than guessing whether the resultant item is based on influences of frequency of data. So when lift is more than 1, the rule is doing worse than informed guessing. Now the mathematics for this grow quite rapidly. The idea behind the co-occurrence table extend to combinations with any number of items, not just pairs of items. So for combinations of 3 items, imagine a cube with each side split into 5 different parts. Even with just 5 items in the table, there are already 125 different subcubes to fill in. By playing with the symmetries of the table, you can reduce this a bit by a factor of 6, but the number of subgroups for cubes of 3 items is proportional to the third power of the number of different items. In general, the number of combinations of n items proportional to the number of items raised to the nth power. So in other words, 5 to the third power is a number we're looking at with trying to look at 3 items of 5. So as you can imagine, this number is going to go very, very fast. Trying to look for, comparing 5 items and trying to predict the 6th item. And the number of items that you have available in your store is thousands. So this gets out of hand. Although it's not obvious when there are just 5 items, increasing the number of items in the combinations requires exponentially more computation. So the result is exponentially growing run times and long wait times when considering combinations with more than 3 or 4 items. So the solution to this is pruning. Pruning is a technique for reducing the number of items and combinations of items being considered at each step. At each stage, the algorithm throws out a certain number of combinations that do not meet some minimum threshold. The most common pruning threshold is called minimum support pruning. Support refers to the number of transactions in the database where the rule holds. So minimum support pruning requires that a rule hold on a minimum number of transactions. For instance, if there are 1 million transactions and the minimum support is 1%, then the rule has to be supported by at least 10,000 transactions in order to be of interest. This makes sense because the purpose of generating these rules is to pursue some sort of action, and you wouldn't develop actions for very rare occurrences. There are 3 important steps and concerns in creating association rules. The first is the size of your item set. Do you want to see patterns for a 2-item set, a 3-item set, etc.? The second is the measure of support you want to observe with interest. And then the third is your confidence or the conditional probability of some item given the certain other items in your item set. Generally, the rules by deciphering the counts in the occurrences matrix and then overcoming the practical limits imposed by tens of thousands of items that might be available in your grocery store or in your item set. So what constitutes a particular item depends on the business need. Within a grocery store, for example, there are clearly tens of thousands of products on the shelves. A frozen pizza might be considered an item for analysis. But is a frozen pizza, regardless of its manufacturer and toppings, like extra cheese, pepperoni, mushrooms, its thin crust, thick crust, etc.? So the purchase of a large whole wheat vegetarian pizza, does that contain the same object as frozen pizza? of a single serving, pepperoni with extra cheese. We have to determine the item granularity that should be analyzed for the right business knowledge to be achieved. That's really important. Because this is the problem with big data. Okay? A typical fast food restaurant, okay, offers several dozen items on its menu, say 100. You're going to McDonald's. And to use probabilities to generate association rules, costs have to be calculated for each combination of items. On a menu with 100 items, how many combinations are there with 3 different menu items if we went with a 3-item rule? The answer is 161,700. That is a huge number of rules. On the other hand, a typical supermarket has at least 10,000 different items in stock, and more typically 20 to 30,000. So calculating the support, confidence, and lift quickly gets out of hand as the number of items in the combinations grow. There are almost 50 million possible combinations of 2 items in a grocery store, and over 100 billion combinations if we went to 3. So though all computers are getting more powerful and cheaper, it is still a very time-consuming process to calculate the counts for the number of combinations. So calculating the counts for 5 or more items is prohibitively expensive. So to use product hierarchies, that reduces the number of items into a manageable size. And that's where we're hoping that you can apply some business rules to that concept. So product hierarchies help us to generalize items in the real world. Items, for example, have product codes and stock keeping unit codes, SKUs, that fall into hierarchical categories called a product hierarchy or taxonomy. Well, what level of the product taxonomy is the right one to use for your model? So this brings up a lot of issues as we look at my example here of frozen foods, frozen desserts, frozen vegetables, frozen dinners. Are large fries and small fries the same product? Is the brand of ice cream more relevant than its flavor? Which is more important, the size, style, pattern, or design of clothing? Is energy saving option on a large appliance indicative of customer behavior? These are all questions that have to be answered. So if I'm looking saying, I just want to know if you bought ice cream, I don't care what flavor of ice cream you bought, or I don't care if it's that you bought Blue Bunny ice cream or Kemp's ice cream. I just want to know that you bought ice cream. Or is it that you need to know who's buying Kemp ice cream? These are choices and decisions you have to make. The a priori technique evaluation offers some advantages. It's well understood, it's easy to implement, and it has many derivatives. The disadvantages is the algorithm can be quite memory, space, and time intensive when generating item sets. So it is obviously really important that we talk about, that concept of how many products are we talking about. All right, let's look at an association rule. And my CSV reader is a little bit different this time. I've actually read a series of items that have been purchased. So just column 0 through, I think it goes all the way out through column 32. And this is what people have purchased together. So citrus fruit, finished bread, margarine, ready soup. So each one of these is a product that a person has purchased. And I've got 9,835 purchase records. So the first thing I want to do is to create a collection column so that the rule learner can learn from it. So what I'm doing is I'm selecting all of the columns that are available in this data set, and then I've checked down here to say create a collection column of type set. And optional or not, I've chosen to remove the integrated columns from the table, so I don't want column 0 through 32. And then I've given it a name, so it's called aggregated values. So now what this data is stored inside of Knime is it's stored as an array. And that's going to be very useful for us for processing with this node. So finally, this particular rule learner This is the one that uses a priori mechanism. There is another association rule engine that it operates differently, and I'm not covering here in this chapter. This is the one I'm going to use. Now, for a configuration, I've told it the item column that has the array in it. I've told it the minimum set size, you have to have at least one value. And the minimum support is 10%. So it has to occur at least 10% of the time, or I'm not interested in this. And that's as a percentage instead of an absolute number. That's how I specified it. Now, the minimum rule confidence I put in is 10%. So I need to know that at least 10% of the time this rule is applying. So let's go ahead and look at the output of this. And I look at the association rules. And what I see is the antecedent. So people who buy root vegetables, for example, buy pastry. Make the antecedent a little bigger. And people who buy tropical fruit buy pastry. And what we want to, of course, look at is the amount of lift. What's the amount of lift we're going to see as a number, as a percentage. So I'm going to go ahead and sort this table, the output, into descending lift sequence. These are my best rules now. People who buy root vegetables usually buy beef. People who buy tropical fruit buy pip fruit. People who buy yogurt buy curd. So you can start to see some of these. People who buy root vegetables usually buy other roots. And people who buy root vegetables, frozen vegetables. So you can start to piece this together, and if you were the grocery store owner, you might start to think about how you're going to package certain sale deals to say, we've got a great deal on beef if you buy, 20 pounds of vegetables, or whatever you want to do with this. But this is how we've generated the rules and how we can set up the update. Remember that if the rule lift is over 1, then the probabilities are overperforming random guessing. Everything below 1 is not. So as I scroll down here, starting down here, these rules start to fall below 1, meaning I'm better off random guessing. And in fact, anybody equal to 1. And when I'm just barely over 1, you're just barely overperforming a random guess. So I start to look for much larger numbers when I start to say my confidence in a rule is actually proving outright. So these are the important columns, like I said, that you're going to want to look at. So, chapter summary. Market basket analysis is a relationship between items. The origin are in retail, but it extends into other industries clearly as well. The association rules are an if condition, which is the antecedent, and then a resulting condition, which is the consequent. The actionable, trivial, and inexplainable are the types of rules you're going to be seeing generated. For measurements, we have rule support, and that is the condition and result of versus total transactions. Our confidence in that rule, the probability of it being reserved, and the lift, the increase over random chance. And finally, when it comes to big data, and process time is going to grow exponentially. So we need small item sets are going to be preferred if you're going to build a model that's even remotely workable. That completes this chapter of the class. Feel free to move on to the next chapter.